It happened about an hour after we shut down last night, and I immediately ordered some sort of mini disc or something that's in the post already. So I think I'm going to need it actually. But fortunately, we also bought a BT SIM just by chance. I hadn't really thought about this. My own phone doesn't have BT, but I bought an extra SIM, you know, as part of the package. Unfortunately, you know, then they made that sort of unlimited for me.
Okay. Yeah. There's Sakura, Simon, and yeah. So what I will do, since this is a discussion, I think I won't mute everybody, so people will have a chance to ask questions. But I think we're supposed to start with Roger giving us the
brief introduction.
A
brief introduction.
A brief introduction, right? Okay, and we'll let the the discussion develop from there. How's that?
Okay.
I have 15 seconds.
15 seconds, okay.
15 seconds. So, but Roger, you have been made co-host, so you'll be able. You can go ahead and share your screen and.
Okay.
And.
So.
So for those of you who are just joining us, Roger Bielavsky is going to be giving us an introduction to complex hyperKähler manifolds.
So
discussion.
I actually, okay, I don't see whether you see what I see.
We see your screen. I see your screen. Sorry.
Yeah, but do you see just one file or do you see all the files?
I see one page.
One page, excellent. Complex hyperKähler manifolds.
Right. Right.
Okay, so hi everybody. So yeah, following Simon's suggestion, I do a brief introduction to these complex hyperKähler manifolds, just so that, well, I don't know if you haven't seen them, or maybe I provide some additional information to Tom's talk anyway. Right, so the complexification of the quaternion algebra, that's 2x2 matrices. Complex matrices, that's what Hamilton called biquaternions. So we define an almost complex hypercomplex, that's really too much to say, so I call it C hypercomplex manifold, if the tangent bundle is the tensor product of the trivial C2 and, well, half-rank holomorphic vector bundle. And then M is C hypercomplex if for every vector, non-zero vector in C2, this rank 2 subbundle is integrable distribution. So we get an action of 2x2 complex matrices on the tangent bundle, which is somehow integrable. So now a C hyperKähler manifold, or C hypersymplectic, which is the terminology I use, and I'll explain in a moment why. So this is C hyperKähler if it is equipped with a holomorphic metric such that for any trace-free 2x2 matrix, we get a closed two-form. So these things were defined by Bailey and Eastwood in 1991. In fact, the paper refers to a preprint from '86, which I think was never really published. But they occurred over years in different guises. I think Maciek and Lionel also had those, but in particular, Jardim and Verbitsky in their work on sheaves on CP3 developed quite a bit of theory of these things. They call it trisymplectic structure generating an SL2C web. So maybe I should say that the reason I here used hypersymplectic, you know, the C hypersymplectic is because hypersymplectic manifolds are based on split quaternions. Right? But if you complexify, then you don't see any difference. On the other hand, this complex hyperKähler behaves much more like an indefinite geometry. So in particular, if you do any sort of quotient construction there, then you run into all those problems that you also have for hypersymplectic manifolds and so on. So, okay.
Can I interrupt briefly, Roger?
Sure.
I think when you say hypersymplectic, you mean in the sort of, I think the older sense of the word that Hitching introduced, right?
Yeah, Hitching, Dancer, Swan. Yeah.
When you talk about split quaternions, whereas now I think it's used in a different way.
So you mean there is a newer concept of hypersymplectic?
Yeah, I think when
so,
you just,
yeah, okay.
you just have a sort of,
I know that, yeah.
I just wanted to point. And the other thing, right at the beginning, when you were saying that E tensor V is integrable, in case it's not obvious, I think that's just sort of saying that the complex structure, that's the 1-0 space for the complex structure corresponding to the choice of the vector V, right?
Yeah, so you choose, so you choose basically maximal torus in your matrices, or Borel, yeah. So Borel subgroup and the I eigenvalue for this will be the.
Yeah. Okay.
Yeah, that's another way of saying this. Okay, so
but actually, is the
time, right? I mean, if
sorry,
you
Roger.
build hyperKähler geometry, then you basically encounter them all the time. But because if you start with the twistor space of the usual hyperKähler manifold, then the hyperKähler manifold is recovered as the moduli space of real sections of this twistor projections with normal bundles direct sum of O1s. But if you take all sections with such normal bundle, not just the real ones, then you will get naturally a C hyperKähler manifold. Right? So, okay, so let me share a few words about twistor spaces of these complex hyperKähler manifolds. So we can define an integrable distribution on X times P1 just by taking this distribution for any non-zero vector V in C2.
Sorry, Roger, can I ask a question?
Sure.
This construction you just gave by taking all twistor lines, would we understand that in the case of the Hitching system, you know, in the moduli of Higgs bundles? Is there a moduli theoretic description of what that is?
Probably, but probably somebody else can answer this. I mean, it's always complexification of your original thing, right?
Right, that's all it is, right? Okay.
But whether you have some other interpretation, I'm not sure.
Can I ask something as well, please?
Yeah.
So is everything you're talking about complexification of manifolds that have SPN holonomy?
No.
Compact.
So if you start with holonomy SPN, then you will get such a thing by complexification.
Yeah, so that was my question.
But it doesn't have to be a complexification.
Okay.
I think in Tom's and Ian's case, this is not a complexification.
It's not?
No, I don't think so.
No, I thought in Tom's case, he's talking about the cotangent bundle of something that's already kind of
yeah, but it's not hyperKähler, what he's cotangent bundle. I will say something about this, but it's a cotangent bundle of something, but that something is not hyperKähler.
Okay, is that something quaternionic Kayla?
No, I think the problem is that sort of horizontally the metric may be sort of will be zero. I think in Tom's setup there's no.
No, I'll say something, but this is not the situation. This is really quite different situation, I think, in Tom's case.
Okay.
The holonomy group is SPNC.
Sorry?
The holonomy group is SPN, C.
Exactly.
Correct. Yes.
Exactly.
Yes.
Exactly.
Yes.
So that's actually it's indefinite. It's got signature 4n, 4n.
Yeah. So you could get different real slices. On some of those it would
Right.
could in principle be hyperKähler, and others could be indefinite metric,
Right.
right?
That certainly happens.
You may not have a real slice.
Right. It may not have a real slice. I mean, the general one may not have a real slice.
True. Yeah.
But how would I know if my one was a complexification of something sitting inside it in a clever way?
Well, I mean, something like this would have to come from a real structure on the twistor space. Yeah?
Mhm.
So if you don't see that, then it's probably not.
Well, but it might be quite difficult to see that, right? I mean,
Yeah.
Well, the other thing is to realize that those real structures are actually totally geodesic in the when they exist, they're totally geodesic in the SPNC. So you could just look for totally geodesic submanifolds of the right dimension, and that's something that can be computed just by differentiation.
Yeah. Okay. Shall I continue? Or more questions? Okay, so we get then so we define this integrable distribution on x cross p1. Well, and if we are lucky and this foliation is simple, then we will get a manifold fiber ring over CP1, which will be the twistor space. Yeah. Otherwise, everything has to be done in terms of foliated geometry. All right, then X is recovered as, well, usually a component of the moduli space of sections with this normal bundle, sum of line bundles of degree 1.
all right, another question. Is that, I mean, if this was the complexification of a genuine hyperKähler manifold, wouldn't the twistor space be Hausdorff? Just by kind of, I mean, could this be an indication that you're not a real guy? Just because the twistor space of a genuine hyperKähler manifold, you just cross the manifold with P1, right? And then put a complex structure on it.
Well, I mean, the real slice, yeah. Well, yeah, no, you're right. Yes, it would be, yes.
Right. So,
but it's not necessarily, well, I mean, it's not a sufficient condition, of course. Yeah.
No, but if you find that your twistor space is horribly non-Hausdorff, then that's probably an indication.
Then yes. Yeah.
No, but how do you know that? How do you know that, for example, if you took a real slice and then you analytically continue the complexification as far as it goes, that will be Hausdorff? It might not be.
Yeah. No, you're right. Yes, you're right. Yes, of course. Yes.
If you're Claude, you only allow civilized complexifications.
Well,
now you have to introduce something else.
No, but hold on a second. I mean, if it is complexification of the hyperKähler manifold, then the hyperKähler manifold has its own twistor space, which is of the same dimension as this.
The same twistor space, isn't it?
It would really have to be an open subset then, this twistor space of the real manifold. Right?
Right.
So I think that this is. So I think, yeah, if it's really horrible, then it's probably means it's not. But yes, okay. But in principle, if you continue too far, you could get something here. Okay, I haven't thought about this one. Okay, so this actually works already for the C hypercomplex. If X is C hyperKähler, then what we also have is an O2 valued holomorphic symplectic form along the fibers of this twistor projection. So this section along the fibers of this. So this M, which occurs in Tom's talk, this is actually one of the fibers of the twistor projection. Yeah, he chose one complex structure, and this was a fiber. Yeah, Z zeta. And we get this projection from X to M by sending the section of the twistor space to the intersection with this fiber. So in particular, for any point of M, this space of all sections passing through the point, this will be a totally geodesic submanifold for this Levi-Civita connection. That's the usual principle of twistor theory, right? It's an alpha surface. You know? So this is this affine symplectic vibration that we get directly from the twistor space. So, okay, so this is essentially what I have to say about generally about hyperKähler manifolds, this complex hyperKähler manifolds. Now, in Tom and Ian have further assumptions, so it's a subclass, right? So let me say a few words about this additional assumption. So first of all, they have additional involution, holomorphic involution on Z, on the twistor space, which covers the involution on P1. And then so that this M is invariant. And then I think by using the connection, we can actually identify, at least in the neighborhood, X with an open subset of the tangent bundle of M. Moreover, I is supposed to, if I is also then compatible with the twist, or this Li is compatible with twisted symplectic form, then the restriction of the metric to M will be identically vanished. And then they have the additional assumption that this Levi-Civita connection restricted to M is flat. I mean, this arises from them, but let's say we assume this, right? That the Levi-Civita connection restricted to M, or the Obata connection, is flat. So what we have actually, M, we have a holomorphic symplectic manifold, M inter, with a flat holomorphic connections, which preserves the complex symplectic form. So let me just speculate that this reminds me, this is somehow, I would like to think of this as a complex analog of special Kähler manifold. That actually what we have is on, so of course there are more assumptions about the lattice action and so on, but I think they might be actually separate from this theory. So I would like to think that what we have geometry of M is this, perhaps with this additional assumption that this flat connection is given by a cubic, by a differential form of degree 3.
I mean, certainly, sorry, the expectation is that if you take, so one of these physicist slices that I kept talking about, so that's really a flat half-dimensional submanifold with respect to that thing Nabla you wrote down. I mean, that's supposed to have a special Kähler structure on it.
Yeah, but M, yeah, I know, yes, but this is not, I am saying that M, your M, not X, that the M is, well, it's not special Kähler, it's a complex analog of special Kähler in this sense. That you have complex symplectic, it's a complex manifold with a complex symplectic form and a flat connection, flat symplectic connection, holomorphic connection, given by a cubic form. And I wouldn't be surprised if then for such thing there is a holomorphic C-map, which then would induce the complex hyperKähler structure on TM.
Roger, are you saying that possibly M is just some sort of complexification of real special Kähler, or is that too naive?
Yeah, I think it might be something like, like the complex hyperKähler is not necessarily a complexification. Yeah? Perhaps complexification of, yeah, no, but you see but I mean, you don't have metric. So if you complexify special Kähler, you would get metric, right? But here you don't really have metric on M. Mm-hmm. What you have is just flat holomorphic connection, which preserves the symplectic form.
But are you claiming that all the data can just live on M? That somehow you can just see, all the data?
I am not claiming any, I'm speculating.
Mm-hmm.
I am speculating that yes, that there is an underlying geometry of M, which canonically gives this C hyperKähler structure on TM.
I mean, the difference here is you have two flat connections, right? Is that right?
Yeah, but the second flat connection arises from the lattice, right? Action, if I understood correctly.
Correct. Yeah. Yeah. And that doesn't interact with the structure in any other way, I don't think, really.
Yeah. So you know, there are all this construction which gives you HyperKähler structure or Kähler structure on the tangent bundle or cotangent bundle. Yeah. Now, I think here there should be also some sort of a construction that you're getting some special, quite special complex HyperKähler structure on the tangent bundle, and that means that there must be underlying geometry on M. So I don't know whether this data is enough, but I could imagine that something like that this could work.
I've always, you know, in the last few days been assuming that M is what we physicists call the hypermultiplet moduli space, which is a quaternionic Kähler, or there's a limit of it, which is hyperKähler, and it's sort of Jacobian vibration over the special Kähler manifold, which is the, say, on one side of the mirror map, the moduli space of complex structures.
Yeah, but if I understood Tom correctly, there's no metric on M.
But also, Bobby, I think that's the wrong dimension, right? Because I think in this theory,
No, it's the right dimension.
The dimension is right, but
is it not the Hitching moduli space though?
okay, yeah.
In the case of class S theory, that would just be the usual Higgs bundle moduli space, right?
Yeah, so I should say that's right. Yes, because in all these, so that's when the complex HyperKähler manifold cannot be complexification of a real HyperKähler manifold, because the dimension can be wrong.
Well, I mean, this one has the right dimension to be the complexification of what Bobby's talking about, I believe.
Okay.
Yeah, exactly.
But it could happen that it has a wrong dimension, because all you need is that the complex dimension is even, but if you complexify real HyperKähler, then complex dimension should be divisible by 4. Right?
I think,
Say that again,
are we confusing M and the tangent bundle of M? I mean, the tangent bundle of M is always a multiple of 4 complex dimensions.
Yeah, sure. Oh, yes, sorry. No, but it's, yeah, but still. So tangent bundle of, I mean, for complex HyperKähler, you don't have to have the dimension divisible, complex dimension divisible by 4. Just complex dimension divisible by.
No, yes, you do, Roger. You have to have it divisible by 4.
No, E does not. Oh no, it does be. Okay, for complex, sorry, for C hypercomplex, you don't have to. Because E could be of even rank, of odd rank, yeah.
But not in this case, not in the complex.
Not in this case, no. But for HyperKähler, for complex HyperKähler, anyway, not, because there will be a symplectic form on E.
Right.
But for hypercomplex, it could happen.
But Bobby, I don't think this can be the hypermultiplet space. It could be the complexification of that, but I don't think it can be that.
Do you mean M or T of M?
Well, really either of them, but certainly, let's say T of M, that's where the hyperKähler structure is living.
Yeah, you know, that I've appreciated,
Right.
but I haven't seen any contradiction to say that M is not the hypermultiplet moduli
Yeah, but
space.
there's no metric on M as far as I can see. Huh?
And, you know, in these kinds of examples, M maps to the, you know, in the class S examples, M maps to the moduli of complex structures on your Riemann surface, which I don't think you would want your hypermultiplet space to do, would you?
I do want that. Want to do that.
Well, maybe you're
So,
right.
I mean, the hypermultiplet, so in the Calabi-Yau threefold case, the hypermultiplet moduli space I'm talking about, it maps to the complex structure moduli space of the Calabi-Yau, and the fibers are the compact intermediate Jacobian. So H upper 3 with values in U1 with a distinguished complex structure on that space.
Yes, but in the example of, you know, these Hitching spaces examples, I believe, would you not be taking the space which is just the Hitching moduli space? You would be taking a base which was, you know, the Hitching base, and then you would just be taking this S1n bundle over it.
Yeah, I'd be taking an S1, I mean, a torus bundle over it, yeah.
But in that setting, you would have fixed the complex structure on the Riemann surface.
Would I?
I think so, but
Well, maybe the Hitching thing, I don't know, maybe that's not the best.
yeah, maybe.
For me, it's better to understand the Calabi-Yau threefold case.
Yeah, it's because the base of Hitching is a complex structure of the spectral curve, and complex structure of the Calabi-Yau is very complex structure of the spectral curve.
Mm.
Okay, anyway, this was all I had to say as an introduction. I think I see Lionel Mason is here, and I think he also has some comments about complex hyperKähler structures. Lionel?
Hi, yeah, I actually took the liberty of just writing something out so that I kind of remembered what I wanted to say. So am I allowed to share my screen?
Just a second, I'll make it. Yes, you are.
Oh, fantastic. Okay. So I think the first thing I actually wanted to say was kind of related to this last discussion. Is that now visible? Sorry, this is.
Yes.
Okay, sorry. So maybe it's a little bit the wrong shape. So the question. So maybe Tom can answer this question. But the does it have a split signature real slice? And the reason I was thinking that is that if you take Z to Z bar and theta to minus theta at the same time, it looked to me like that was a real slice, but I might be just missing something stupidly. What do you think?
Yeah, I'm not sure. I would have to think about that.
Okay, well let's fantasize for a moment and assume that's true. Then that then gives me an excuse to.
No, but Lionel, all the examples Tom had do have real slices because they all depended on the coordinates, and all you do is you force these coordinates to be real, and that gives you a real slice.
Yeah. I mean, okay, that's very good. Thanks. Okay, so this then goes back to a game that Claude Lebrun and I were playing sort of through the noughties, where if you have a split signature real slice, then you can still define your twistor space, you can and everything, but the twistor space now has a totally real slice in the sense that there's a complex conjugation involution on the twistor space which fixes TR. And then instead of looking at your twistor lines, it turns out that you actually really want to look at holomorphic disks with boundary on this real slice. And we were really exploiting the fact that analytically, this is, you know, so split signature you think of as being a horrible thing to play with analytically. I mean, there's no positivity or anything. But it turns out that if you start playing this game, then you can use a lot of compactness theorems on holomorphic disks, and you can do a lot of analysis.
Yeah,
and so we
interrupt for a second.
Sorry.
I mean, if you take this real slice, then the twistor space is the same, no?
It has a fixed point of the involution if the
that's what you mean. Okay, yeah.
So PR is if you have a Euclidean sort of reality structure, then the complex conjugation has no fixed points.
Yeah, sure.
If you have a signature involution, then it has a nice real slice, and then what you discover is that there's some interesting double cover behavior and so on, and you have to consider holomorphic disks. The Riemann spheres, they don't just double up these holomorphic disks. And but anyway, you can do some nice analysis, and we were able to prove some theorems about Zoll manifolds, which were very nice. I mean, we had a lot of fun with them. Whether it has any connection to what Tom and friends are doing, I really don't know. But anyway, okay. So that was the first thing. Sorry, I have 4 discussion points. That was the first one. So that was just a fantasy that there might be some connection there, and I don't really know if there is or not. Okay, so the second one really goes back to Maciek's thesis, I think, because I'd just seen a lecture by Krichever, I think, just before I had to try and think about what we might work on. And Krichever was talking about the geometry here. So all of these geometries that sort of these joist structures, Bridgman, Strawn, and so on, they all have misasymmetry. So in fact, and as far as I know, the symmetry sort of, it doesn't have a huge fixed point set. I mean, it does on the Riemann sphere, of course. It has a fixed point set at 0 and infinity, but in the total twistor space, it doesn't. And so you can quotient by the symmetry, and then you get a nice Einstein-Weil space. But it has, so this is if you're working in 4 dimensions. We were only, Maciek and I were only really thinking about that. And so that gave rise to an Einstein-Weil 3 space by all results of Nigel Hitching. But it has some extra structure, which was some congruence, where I think I'd had to ask Maciek to give you the full details as to what the congruence was doing. But basically, this reduced twistor space has a Poisson structure, or a symplectic structure. It has a holomorphic symplectic structure that's meromorphic. It has so these were things we were playing with back then, and they were really designed to sort of relate to the kind of structures that were coming up out of Gromov-Witten theory and Seiberg-Witten theory and so on. And these all have hierarchies, and the hierarchies all have roles in those stories. So anyway, so that was the second thing that this brought to mind, was just games that Maciek and I were playing in the 90s. And of course, Ian Strawn was with us back there, and playing with the corresponding stories for Frobenius manifolds and such like. Anyway, I don't know how much that will connect, and I don't know if it's very useful, because often it's, even if you have a symmetry reduction, it can be useful to work on the larger space and so on and so on. Okay, so I'll, unless anybody's got any questions, I'll move on to the third topic, which was sort of, so I think Tom was asking, what are these generating functions? What are they doing? And so this is a question that we were asking back then, really. These were all Tau functions for integral systems, and everyone was looking back to Siegel-Wilson, and they were looking back to Jimbo and Miwa for these things being correlation functions in some 2-dimensional quantum field theory. And so what's the twistor interpretation of that? And so again, at the end of the 90s, in 2000s, we were able to see that, well, we were thinking more in terms of these being Tau functions for KdV. We now are understanding from Tom that we should be thinking harder about Blavatsky type functions rather than Tau functions for KdV and whatnot. And so in those days, we look back and we gave a kind of a quantum field theory of sections of, so when you think of these as reductions of solutions to KdV equation, then you have a Ward bundle on twistor space, and there's a quantum field theory of holomorphic sections of the Ward bundle over the lines in twistor space. So we were able to sort of establish a story along those lines that would be the twistor interpretation of the Tau functions. But just this last year, in a completely different format, with Tim Adamo and Atul Sharma, we were looking at the Blavatsky functions. And just to give a little bit of background, we were trying to compute scattering amplitudes for Einstein gravity in 4 dimensions. And it turns out that the Blavatsky functions play the role of a generating function for those amplitudes. And we wanted to compute them in twistor space, and we wanted to do it using a version of twistor string theory. And so then what you can deduce then is, So it turns out that the Bansky functions, you might have thought the Bansky function is a function on spacetime. Each point in spacetime corresponds to a Riemann sphere in twistor space. So you might have thought that the Bansky function might have something to do with the action of that Riemann sphere. That might have been a guess. But the question is the action of what theory? And so it turns out that it's not, so the first guess might have been that it was a twistor string that Witten introduced in 2000 and 2003. But it turns out it's not that action, it's a different action. And so we wrote down new twistor strings in twistor space whose actions give rise to the Bansky functions. And you can do it for both the first and the second kind. And the two different kinds correspond to two ways of presenting boundary conditions for the, if you want to write down an action for it, you had to impose boundary conditions on the line and so on. And so for us, this was meant to be a new derivation of four-dimensional Einstein gravity scattering amplitudes, and it does that, and we were quite pleased with that. But I sort of pleased also that it has some connection with the story that. Well, I still don't know. I don't know whether that interpretation would be of any help in the story that Tom's been telling us about, but you never know. There could be some application. Okay. So there's only one more thing I wanted to talk about, but in many ways, I think this is the most interesting thing, and it's the reason why I've got excited by this topic and why I've been reading avidly Tom's papers over Christmas and hope to talk to them some more. And this is actually a story so this is a story I've been investigating with Hadley Frost, who's a graduate student of mine who's just finished. And it's a story which started about 12 years ago. And this was a computation of scattering amplitudes at strong coupling now. So this is an ADS-CFT story. And it's very difficult for me to summarize this all in one go, but you have a problem of studying minimal surfaces in ADS. And it turns out that that is a Hitching system, but with the wrong real form. So the real form is not the standard, it's not a harmonic map into the complexified group divided by the compact group. For ADS3, it's a harmonic map into SL2R. It's a Shine-Gordon equation. And you have very specific boundary conditions for this minimal surface that go all the way out to infinity. And it's a beautiful story. And they were very lucky because they had Gauto, Moore, and Liedtke, or at least they had Gauto down the corridor, I think. I think Gauto was in Princeton at that time. And it turned out that the analysis you needed to use to study this minimal surface problem turned out to be exactly the same as the GMN analysis, or at least close enough that they could sort of pickpocket many of the structures. So your problem is to specify the boundary conditions for this minimal surface, and then to compute the area of the minimal surface as a function of the boundary conditions. And it turns out that the boundary conditions are essentially n naught n. So you could think of the boundary conditions as being the space of boundary. Sorry, here I'm working with a cut down ADS3 problem, just to be simple. So the boundary conditions could just be taken to be something in the AN cluster variety. And you want to find the area of the minimal surface as a function on this cluster variety. And so this could be represented as a Hitching system, and they did this. And in fact, you're looking at this Z2 invariant slice that Roger was just talking about, that Tom and Ian have, and so on. So it's really this kind of special Kähler slice that they're working on. And they need to compute the area as a function on that slice. And they do it by constructing really, well, okay, so the Y system, I can't tell you what a Y system is. This is something developed by Zamolodchikov to study integrable models in integral QFT. And it involves a system Y, which is basically a set of cluster coordinates on AN, and it depends on the spectral parameter. And it satisfies the analytic conditions, which would somehow tell you that you're trying to find a global line in the twistor space. Anyway, so I was reading these papers over Christmas and reading Tom's papers, and as far as I can tell, at least the A2 cases are the same. So it leads one to optimistically think that the AN cases are the same, and maybe the grown-up case is the G4N case. That's the one, or maybe probably G4/4N. And then an even more grown-up case would be to go beyond strong coupling and to go to finite coupling. So that maybe you need some extra quantum stuff there. So anyway, so I think there's some beautiful connections with completely different physics areas than the ones that have been discussed so far. But it's all a little bit conjectural, and I've had a few drinks, and so I'm probably being a bit more assertive about it than it's due. So I'll stop there anyway. So thank you for giving me the space to talk about this.
Well, thank you. Okay, comments?
I have a comment about Plebanski's function. Can you hear me?
Yeah, sorry, yes, yeah.
I mean, it partly hoping to answer the question Bobby asked today or last time. The question was, I mean, what's the physical interpretation of the Joyce function, which is how Tom and Jan calls it. So, you know, points in X, so in the tangent bundle to M, correspond to these rational curves, the twistor space. And we might ask, how do you construct these rational curves? And you can set things up so that this the Plebanski or the Joyce function is in fact a function on the twistor space, and you set up a Hamiltonian system where this function is a Hamiltonian. So there is a procedure where you build the twistor curves.
You're taking me back
by solving Hamilton's equations, and in these equations, the coordinates which Tom called z's are the positions, and the thetas are the momenta, and the w is the Hamiltonian. So we can, I mean, I know how to do that in dimension 4, and I expect this is a feature which you can extend to 4n dimensions. That's all.
Mm-hmm.
Yeah.
That was describing the twistor lines, the flow of this Hamiltonian?
That's correct.
Well, you need to make it depend on the zeta to do that. So I guess the way in which I was formulating it in this work with Tim and Atul was to say that you have to look at the whole. I mean, the easiest one is the first Plebanski function. So the first Plebanski function, you've got a twistor line, and you specify its boundary conditions in 2 fibers of twistor space. So you had Tom's variously t h bar or epsilon equals 0 and infinity, and you fix the position of your twistor line there, and then once you fix that position, you can compute the action of the curve according to a kind of a twistor action, and the twistor action is simply built out of the holomorphic Poisson structure on the fibers of the twistor space, and so in that case, it's a generating function. It's a generating function that takes you from the point on the first fiber and its first derivative there to the coordinates made at the other end. The other end there. So you've got the point in that fiber and then the direction there. So it's a generating function taking from one canonical coordinate system to the other. Whereas in the second kind, you have you have the fiber, you have the first derivative, and then it gives you the second derivative instead of in terms of the first and the.
So I think so. You can set things up so that your 2 fibers come together, and rather than looking at coordinates on 2 fibers, you look at the coordinates on 1 fiber and first jet, and so there is a precise sense in which the second heavenly equation is an infinitesimal, but still nonlinear version of the first heavenly equation. So, you know, the Hamiltonian is an infinitesimal form of your generating function, I think.
So related to that, when you were talking about gravity amplitudes, Lionel, so when Antoniadis, Gava, Narayan, and Taylor first computed the kind of generating functional for the f sub g's, it's actually, I mean, it is in the context of supergravity theory, but the way they did it was to, I mean, the physical interpretation of what they did is those are the coefficients of terms in the effective action of, you know, certain four-dimensional supergravity theories. So,
me, that sounds like a much more
is your twister theory that you were talking about the thing which is sort of just, it's another gadget for computing those things?
So in the, sorry, you're talking about something that sounds more grown up. You're doing a proper quantum field theoretic calculation where you're summing up over instance on contributions, and that sounds like an amazing calculation. The sort of thing that I was doing was to say that I could expand self-dual gravity. So the hyperKähler equations are the self-dual sector of full Einstein gravity, and I can expand around the self-dual sector, and so I can use the twistor correspondence just to sort of talk about a certain number of negative chirality particles on that sector. If you just have two particles, then you're in the kind of world of Lubansky, where you are fixing two fibers of your twistor space. You know, just the momenta of those particles fix those two fibers. And but if you have many particles, then you start fixing many fibers. But and then you need higher degree curves. So
yeah. So it sounds exactly like that, because actually the way they computed it was to switch on a self-dual, self or anti-self-dual, depending on their conventions, background.
Oh, I see. Well,
with more and more particles or fields actually added to the, sort of labeled in degree by the number.
Oh, amazing. Okay, so
the number of particles corresponded exactly to the genus when you refer to when you translate it back into Gromov-Witten invariants.
Oh, well, I'd love to try and make contact with that story. So if you could fire me a reference, or maybe I can just write down the names.
There was a couple of papers by Antoniadis, Gava, Narayan, and Taylor in the mid-90s.
Gosh, okay. Yeah, I'll check them out anyway.
It definitely sounds like this twistor string theory that you were talking about is a kind of I don't know, kind of zero mode limit of what.
Yeah, so the twistor strings are just characterizing the rational curves in the twistor space. That one's after one, one's.
Cool.
So you reduce everything to d-bar problems.
So does anyone can say something else about complex hyperKähler?
I have a question. I mean, can anyone imagine the relationship? So, I mean, I discussed some examples that were sort of indexed by the same data as the Hitching system. I mean, admittedly, I was just doing rank 2, rank 1, but you know, I had the, you know, all the same data was coming in, a Riemann surface, and you know, I ended up considering the space of quadratic differentials and so on. So there's obviously some relation to the usual Hitching space, but I'm getting something twice the dimension, and somehow I'm getting something where more related to the universal Hitching space, where I vary the complex structure on the curve. I mean, can anyone imagine how these things can be related? It seems strange to have two things, you know, both hyperKähler and both depending on the same data. And it would be nice to understand the connection between them somehow.
So it wasn't just simply this semi-flat limit then? You think it's something more?
Well, I mean,
he has twice the dimension of the semi-flat limit.
But the semi-flat limit was the special Kähler, was it? Or was it the full thing? I mean, special Kähler determines a quaternion, a hyperKähler, doesn't it? It's just that you don't usually talk about it, because if you're in the world of Seiberg-Witten, you're only interested in special Kähler for your...
Yeah, but then Lionel, take that hyperKähler and then take the tangent bundle of it. So
yeah,
the line.
Yeah. So the hyperKähler space is the... Yeah. Okay.
I mean, we have this very explicit description in the A2 case, so any conjectures can be checked. But,
well, it's the same as Fernando's A2, I think. Except, no, actually, he didn't do the decagon. So Fernando did the octagon, the hexagon on the octagon, but he didn't do the decagon. So your A2 case is the decagon, and yeah, I'd hesitate to say it's absolutely the same as what you're doing, but it looks identical to me.
I know something which might be at least in the same vein as what you described, Tom, but let me say it. There's a Hitching hyperKähler metric, more or less, on the moduli space of representations of a surface group into SL2C, which depending upon a choice of a Riemann surface.
Ah, okay, that sounds promising. Where might I read about that?
Well, am I saying it? I mean,
oh, sorry, this is the usual one.
The usual one, yeah.
Yeah, sorry, yeah, this is the usual one, yeah, okay.
The usual one. But there's another one, which is sort of a universal one, you might say, at least on an open set of representations. Or you can think of it as on, you can also think of it as on the cotan, on the space of quadratic differentials.
So, sorry, can you explain more? The first one was representations into SL2C, so the character variety.
Right. And then, okay, there's another one, which is in a sense a universal one, which you can also, let's see. One way of thinking of that is the general result. If you have any Kähler manifold, it has a thickening to a hyperKähler manifold as the fixed point of a circle action.
Okay, I can imagine.
I forget whose.
Oh, that's Fikes and Kaledin, yeah.
So that's so it's kind of a general. So for that, you take the Weil-Petersen metric on the moduli space of Riemann surfaces. And then that will automatically produce this hyperKähler thickening on a neighborhood in the cotangent bundle.
Okay.
But you can also describe that in an explicit way. There's a nice way of saying it, which I don't remember. So in one complex structure, you can think of this as the product of two copies of the moduli space, or at least a neighbor. So you take a pair of Riemann surfaces, which are sort of not too far apart. Then there's the general fact that there's a hyperbolic three manifold with two boundary components, and the conformal structure on the boundary components is the two given ones. There's a kind of a hyperbolic cobordism between them. And then if the surfaces are not too different, then there's a unique minimal surface in this hyperbolic three manifold, so in the middle. But this hyperbolic thing becomes infinitely large at the ends. So in the middle, there's a minimal surface. And then you take the area of that minimal surface, and that gives the Kähler potential, which defines this hyperKähler metric. But, well, I'm not sure it has much anything to do with it, but at least it sounds, it is, at least on an open set, it is a metric which is sort of also hyperKähler, but somehow different from the ordinary Hitching ones. It doesn't depend on the choice of complex structure.
Useful fact.
Sorry, what space was the minimal surface in? Again, I lost track.
Hyperbolic 3 manifold.
It's on, you can think of the space either as a neighborhood of 0 in the cotangent bundle of the moduli space, which is to say a Riemann surface and a quadratic differential. Or in another complex structure, you can think of it as a neighborhood of the diagonal in the product of 2 copies of the moduli space.
But it should be actually one of the copies should have opposite complex structure or not? One of the copies should have the negative complex structure.
Probably that's right. Yes, you take m times m bar. That's probably the yes. That's right, because in this hyperbolic cobordism, the orientations on the end are sort of different. This is a deep theorem in complex analysis called the Baer's simultaneous uniformization theorem, that you can produce this hyperbolic, because it means there's a representation in this hyperbolic 3 manifold is given by a representation SL2C. And it's somehow, well, it's got to produce, it's got to be quasi-Fuchsian, I think is the word, to find these Riemann surfaces, something like that.
That's pretty interesting. There's, you know, that there's this whole cluster story, the cluster structure on the character variety, which was introduced by Fock and Gontrov. They also used this Baer's double uniformization thing because they were describing, there is some kind of double cluster algebra, double cluster variety that they consider. And to interpret that, they exactly use this theorem. So, and that's, yeah, I should have a think about that, because that is double the dimension to the usual cluster variety and so on. So it has this flavor to it. Yeah.
Good. Further questions, contributions?
I don't know if it helps, but just trying to understand Tom's 2 examples. The thing you called doubled A1, which I didn't really understand, but I understood the pre-potential eventually. I mean, that the pre-potential you got at the end of that was essentially the leading contribution to the pre-potential of the conifold when you are close to the conifold singularity. At least that's physically how we think about it. But then the second example was the sort of resurgent analysis of the resolved conifold on one side of the mirror map. So in both cases, you have the same dimension, but I was getting, because I'm a physicist and we, in your language, center set W equal to 1. So for me, the conifold has a one-dimensional space, but you are doubling it in the way that when we think about it, it's a difference just between homogeneous and projective coordinates on the complex structure moduli space.
Yes, I think you're right in all. Yeah, that's all sounds completely correct. I mean, the difference was, of course, that in the first case, exactly as you say, we're sort of looking near a conifold point, which means, I guess, that we're just looking near where a 3-sphere shrinks to nothing, right? So yeah. in A model terms, we're just looking at a category generated by a single 3-sphere.
But so would you claim that the answer you got there in the first example would be the full answer for the deformed conifold then? Is, you know, is this the cotangent bundle of S3, everything contractible to a 3-sphere? I should have asked that during the talk, but I didn't.
Is that right? So the deformed conifold is just the cotangent to the 3-sphere?
Mm-hmm.
And that just has a single object? I guess it does. So yes, probably.
I mean, single compact object, but
yeah.
You know, of course, you've got non-compact Lagrangians as well, of course. But.
Mm-hmm. Yeah, I mean, that's how you should think. I think that's how you should think about the extra, that gamma dual that I had to introduce as some kind of non-compact thing that's coming in and hitting the sphere.
Okay, yeah, it's just the, yeah.
There's no brain, you know, there's no BPS associated with that, but it's just handy to bring it along so you can see the action on homology.
Well, yeah, there's no finite mass BPS guide, but in the story, you know.
The second example to me is much more complicated because there are many more objects, right? Instead of just having a single spherical object, you've got a whole Z worth of spherical object and a load of other things as well, you know, the points as well. All right.
Yeah, I mean, it was interesting, you know, seeing the formulae that you wrote down. I hadn't appreciated that you wrote a paper about this like 3 years ago or something, or even longer ago. Just the, I mean, the formulae that you were getting, you know, I've seen those umpteen times in one form or another in the physics literature. So it's very interesting that you're able to kind of establish, even, you know, including the zeta of 3 and there's a sort of I pi over 12 term.
Yeah, it seems to fit very well, doesn't it? Yeah, and this particular non-perturbative function I have also appeared in the physics literature by Hatsuda.
What's a Hatsuda? Okay, I should look at that. And the reason that you didn't want to include compact divisors because those would lead to this. Those wouldn't have the property of what you call decoupling. Is that the reason?
Yeah, correct. Yes. So those are harder, and you know, I think, I mean, so that yeah, those are harder. And that last class of examples I was discussing relating to Hitching systems and so on, I think that's an approach to some more realistic kind of CY threefolds. I guess as you know, as we'll hear in Jona's talk tomorrow, that you know, I think you can approach some more interesting Calabi-Yau threefolds using tau Pan-Lavie tau functions and so on, which fit into that last story I was talking about.
Okay, well, that's very interesting. Oh, but the entire function that Marcos was talking about in his talk is in principle a conjecture for what the answer is for P2. I mean, O minus 3 of P2.
Yeah, and that example, you know, I mean, we love local P2 because it's a very nice example you can try and compute with, but the sort of things Marcos was doing seem way out of reach for us. You know, I mean, that's I mean, even just the DT theory of the local P2 is very complicated. I can't imagine, mind you, maybe other people can, so I should just say nothing.
Yeah, but I would like to hear why you think it's very complicated from your point of view.
Well, these examples coming from quadratic differentials are what we would call tame, I suppose. The BPS invariants are all either 1 or -2. All the moduli spaces are just either points or P1s. And you know, there's basically only one thing on each ray, and the rays are almost never dense. You know, this diagram of BPS rays I draw, they do get dense, but only in one particular way. Whereas on local P2, you get dense rays all over the place and BPS invariants of all different types. I mean, it's a much more complicated example. The BPS spectrum is just massively more complicated, I suppose, is what I would say.
Right, okay. But I thought Marcos had a quote-unquote peacock diagram for that case as well. That didn't look terribly dense, but maybe I was misunderstanding.
I mean, I think he was just drawing part of the diagram, maybe. I mean, I'm not completely convinced by the peacock terminology. I mean, if you take a rank 2 lattice and map it into the plane, aren't you always going to get a peacock? I don't know.
So something else occurred to me. So the fact that your twistor space has this involution, which keeps 2 fibers, that reminds me actually of what Nigel Hitching was doing for folded HyperKähler structures.
For what, sorry, for?
Folded HyperKähler structures.
Mm-hmm.
So that's his paper on diffeomorphism groups, Hitching systems and diffeomorphism groups.
Okay.
And he has something like that there.
I mean, the other thing I should say about this twistor space is that the other condition we are putting on is that the existence of this vector, Euler vector field, whatever, this kind of.
But it's not given just by rescaling, differentiating rescaling along the fibers.
Well, exactly. So it will identify all the twistor fibers apart from 2, if you see what I mean. So there's, so it rescales the base of the twistor fiber.
Okay.
So
the base is in a way conical.
Yes. So there is a single point at the origin, which is what you showed in your picture. That one of those is M. One fiber is M, but the rest of the fibers are all identified and they're not M.
Yes, sure, I understand. But this is similar to what Simon was saying in this situation, where you have one fiber where this is a cotangent bundle, and all the other fibers are identified with M cross M bar. Yeah?
Mm-hmm, mm-hmm.
So that's.
I mean, the other thing I would like to see is just, I mean, it would be amazing if people who were better at calculations than me could actually calculate some of these things. So I did actually, in the A2 case, calculate this Joyce function, and so these are kind of explicitly describable, these structures, but and I suspect I'm not the right person to calculate these things, but there's the whole sequence. There's the AN sequence, which is spaces of polynomials. There must be a structure there. Well, I mean, I expect there to be a structure there, and it presumably has a Joyce function, and one can try to understand these spaces, but I don't know. I mean, Lionel seems to suggest that maybe they're already known, but I don't know how explicitly they're already known.
No, they're not known. I mean, I think, as I said, Fernando went as far as the hexagon. The A2 case is the decagon. So maybe he did the octagon, and there was some Panleve transcendent for the octagon, but maybe that was only the symmetric one, the cyclically symmetric one.
Mm-hmm.
So,
well, what's the relation between these polyhedra you're talking about, Lionel, and Calabi-Yow's?
There's no apparent connection whatsoever. I mean, this is just the Hitching system you get from the task of finding minimal surfaces in the moduli space of the Hitching system of minimal surfaces in ADS3 for the AN case.
Okay, so you're talking about Lorentzian light-like polygons as the boundary of the Riemann surface.
With light-like polygons in the boundary. And
okay.
So that's what the decagon, so they have an even number of corners, and it's So it's really sort of M05 for the decagon, and this Levy transcendent gives you the way that the scattering amplitude is behaving at strong coupling. And so it's a long way from Calabi-Yau stories. But on the other hand, people have been using...
But not necessarily. I mean, often the Riemann surface turns out to be kind of related to the spectral curve, which itself is a Calabi-Yau, is the retraction of a non-compact Calabi-Yau threefold to its compact, retraction, which is then the mirror of some kind of more natural or more kind of obvious Calabi-Yau threefold.
Right.
That's often how these things seem to work. But
so you're talking now in the world of GMN and invariants and so on.
Yeah, yes, and sort of a little bit beyond that as well in some sense. But
I mean, this to me, it still seems a different world. You're computing a different object. These amplitude are not effective potentials. They're functions of kinematic data, and so the interpretation of the cluster algebra in this case is as a receptacle of the kinematic data, and so the maximally symmetric super Yang-Mills in 4 dimensions. The cluster variety in question is G4n, or probably, if you want to have the whole thing, it's G4/4n or something. There's some supersymmetric dimensions, but you could get away with G4n for the MHB part. So that's presumably a rather ambitious thing to look at from the perspective of Tom. G4n as what would the corresponding space? What would that look like in your world?
I don't remember what the quiver for G4n is, but
it's some sort of three rows and Actually, Hadley was saying you've also got some diagonal lines as well. So I thought it's just a grid with sort of 3 rows and then maybe diagonal lines as well.
Yeah, no, that sounds quite ambitious. I just wanted to mention this. You mentioned this Y system. So there's a paper of Gaiotto where he explains the relation of the Y system to these kind of Riemann-Hilbert problems that I was discussing, and I guess he thought about before. So if presumably you know about that connection, do you? But in this paper, Oppers and TBA, he explains how the conformal limit, which is what I'm studying, is related to the Y system. Actually,
okay, so I wasn't aware of that. I mean, I'm pretty sure that Fernando and Juan learned about Y systems from Gaiotto. They were just very lucky that they had Gaiotto down the corridor who could tell them how to solve their system. Although their papers are wonderful anyway. I mean, they're beautiful. They do it very nicely, and I don't know how much help they had.
Other contributions, questions?
Can I ask, Tom, I mean, you had your examples where the metric was flat. So that was just computing directly the curvature, and if there's a polynomial or something, I mean.
It was just that the Joyce function, the Plebanski function was cubic, and the curvature is given by the 4th derivative. So.
Right. But then do you have a sort of another class of examples where it's quartic or something, or?
No, I don't see that. I haven't seen those, but I mean, as you can, it would be nicer to give this talk if I had more examples. So I have those ones that are flat, and I have the A2 one pretty explicitly. But other than that, I have a nearly finished construction and no more explicit examples. So hopefully that can change, but yeah. But no, the one that's not flat is not polynomial in theta at all. It's just
yeah, I remember.
So of course, Zamolodchikov had his ADE Y systems as well. So I mean, And I guess that there's a world that studies these things in the context of cluster algebra. So do you know if there's any connection there with your the corresponding story that you might develop, Tom?
I mean, I don't really understand what the Y system is, but I mean, is it that? I mean, one thing I can look at is that sort of the solutions to my Riemann-Hilbert problem give you maps into the cluster variety, and you can take my parameter epsilon t, or whatever I call it, epsilon, to infinity, and there you will have to land at somewhere at a point of the cluster variety that's kind of fixed by the automorphism obtained by composing all the wall crossing things in a circle. And so, for example, in the A2 case, it means that, you know, your coordinates, your cluster coordinates satisfy, you know, are the golden ratio, for example, right? So you get these kind of algebraic equations for your cluster coordinates, and there are just some finite set of fixed points. And I think that's what the Y system tells you about, somehow those fixed points as epsilon goes to infinity. So I could be wrong about that, but that was my interpretation. So, so you know, it doesn't really contain enough information to tell me the sorts of things I need to know. It's a sort of limit.
Yeah, I found the Y system a bit difficult to parse because some of the relations that they write down are kind of very trivial ones, which are just like the Blücher relations or something. But then they express the analytic conditions for globality. So in some sense, they have a way of expressing the condition that the Riemann sphere is global, so that's what actually gives it teeth. But I've never really found a good way of understanding how it is they're doing that.
Okay.
So what you're saying maybe a more detailed understanding than I ever arrived at.
No, I think I should look again and see exactly what it is. Yeah.
Lionel, I just wanted to stress what I was saying earlier about the relation to amplitudes and the topological string.
I mean, this sounds fascinating. I mean, surely these things are effective. These are effective potentials rather than amplitudes. Are they? Or sorry,
So if you have a physical, you know, if you have if you're able to understand the exact low energy effective action, or what Greg calls the low energy effective theory, then you essentially write down coefficients of higher dimensional operators. And the ones I was referring to are higher dimensional operators in which you have certain powers of a self-dual curvature in 4 dimensions, contracted with a number of spinor fields of a fixed chirality, or helicity, if you like.
I think I can understand.
So if you were to compute the amplitudes for those fields in that gravity theory, then the answer would simply be essentially be proportional to the coefficient, the absolute value of the coefficient squared. I mean, sorry, the actual probability would be the coefficient squared, but the actual amplitude would be proportional to the coefficient. And I have a feeling that that's what your twistor string theory provides.
Well, I should check it out. I think I see what you're saying. The effective action somehow is a generating function for the scattering amplitudes if you for the all pass amplitudes.
Yeah.
That could be right. I'll check it out. I think I've identified some papers from the early 90s by Hamiltonian on this. By you.
But yeah, so I mean, in those papers, they essentially compute the exact effective action for those, for those operators. in the.
Multiply corrections to gravitational couplings. Is that the right type of type?
Yeah.
I'll check the maths and see if I can understand them.
Well, if you have any questions, you can also email me, and then I'll.
Yeah.
Yeah.
That'd be very helpful. Thank you.
Good. There are still 10 minutes planned for this discussion. So. Can anyone think of something? Question? Or?
Maybe the time has come to stop the recording, at least.
Yeah.
Okay. And okay, the recording is stopped. And also the streaming, I guess.